Welcome to our second part of our ESR deep dive session. Okay, so we have done all the theory, or most of the theory, to understand a bit more what we are doing. So let's go, as promised, into experiments. And we just start off here with the question, why can we test electrolytic capacitor in circuit? And you see I have here 470 microfarad 25 volt capacitor, and we already reading our ESR, but something is wrong. If you watch our frequency, our test frequency, we know it is only 1 kilohertz, and that's too low. So let's change our frequency to 100 kilohertz. And you see our reading has changed. And now this capacitor is in spec, but tested with 1 kilohertz, it is out of spec. So let's take here our universal table, and 470 microfarad 25 volt should be, oh, it is not in spec, but anyways our table is telling us 0.12 is the maximum what a 470 microfarad with 25 volt should show. And it is showing a bit more, so this capacitor is for really a very long time here in my shelves. So it has already started aging a little bit. And to be honest, if we would found a capacitor like this in a working circuit, which we use on a daily basis or so, I would swap it out. This one has never been used. It is MOS, and so it can be reformed a little bit. So you may know that we can reform electrolytic capacitors, so that is possible, but that is for the moment in time not our question, what we wanted to test out. We want to know why we can test a capacitor like this in circuit. And of course there is only the capacitor for the moment in time, but we want to know what happens if we put, first of all, so this here is a 1 mega ohm resistor. So what happens if we put this, oh, this one seems to be, it was in a circuit, so we have to cut it here a little bit so that we get it here into our breadboard. Okay, so let's put it in parallel, and you see that our reading is the same. So even we have now here our 1 mega ohm resistor in parallel, no change. Okay, so you may say, that is quite a huge resistor, so let's try with a lower resistor, and this is a 330k resistor, and we leave the 1 mega ohm here in our circuit. I hope that the light is okay, that the contrast is fine. I do not really see it here on my little screen. Anyway, so let's put this one in parallel as well, and let's see what's happening here to our figure. Nothing. So it is really staying the same. Okay, let's take another one which we put in parallel here, and that is a 33 kilo ohm one. So we are going down with our resistor value, and it is, yeah, it has changed here our last digit, but that can be something different, not necessarily here our resistor. But anyways, one digit is no change at all. Many ESR meters only have two digit, so you only would see two digit, and this one has a resolution of 3. So anyways, it is the same. So let's go with a 150 ohm resistor in parallel, and let's see what's happening. Really nothing. Okay, so now I have no space anymore, so let me take out here our 1 mega ohm. I take the 1 mega ohm out, and I have here a 10 ohm resistor. So that is now really a low resistance what we put here in parallel, and you see it is in, and yeah, now you see a little change here. So you see that it dropped down to 0.156, but only here in the 1 milliohm area. So that is almost nothing. We still can determine if this resistor, if this capacitor is good or not. So what's really going on here is very easy to tell. The capacitor with its ESR is the lowest impedance in circuit, and even you put a very small resistor in parallel, the change here is not significant. So that means if there are no other capacitors in parallel, then you can always use the value what you have seen here as real value, right? If you have a couple of capacitors in parallel, then you always would read the lowest impedance, and you do not know if one of the capacitors which are in parallel are good or not, because you wouldn't see, right? You wouldn't really see the high impedance if there are more than one is in parallel. So that is what you need to know. So just check your circuit, and when you see that there are more than one are in parallel, then you have to do it in a different way. Then you really have to take the capacitors out to make sure that all the capacitors are just fine. But you can see here, as long it is the lowest impedance in circuit, you really can test it like this with other components in parallel. And if there is another component in series, so that wouldn't make any difference at all. So that is the proof that it is really working in circuit as long there are no other components, other capacitors in parallel, right? But let's do it here with a real circuit. So let's say this here, it is 560 microfarad capacitor with 35 volt. All right. So let us simply test this capacitor in circuit as it is, and we are waiting for a reading, and here it is. So we are reading nothing. Okay, so maybe that the both contacts get together. Let me see. We can manage it, I hope. All right, so we have here 15 milliohm of this capacitor, and the question is, I mean, this would tell us this capacitor is just fine, nothing wrong with it. It is a very good reading, so the capacitor is healthy. But let's take it out and let's see if our reading is more or less the same. And you see this capacitor has here a scratch, so we cannot swap it with a good one out of the shelf. So when we take it out, you can see here with the scratch, it is definitely this capacitor, and it is a Rubicon. Is it a Rubicon? Yeah, yes, it is a Rubicon. So let's simply take it out here. Let me see what we can do here around the camera. Hope I can find now the right solder joint. It's a little bit funny here around the camera. Let's try. Let's try if we have here the right one. Okay, so I have here the capacitor. Here it is with our marks. And let's see what we can read now. Nothing. That is a good demonstration. Oops. Come on. And we really have a low reading as well. It changed a little bit, so you see that we definitely have components in parallel which are influencing our reading a little bit, but more or less it is the same value. And in circuit we already said this is really a good and healthy capacitor, and now we can say the same. It is a good capacitor, and I guess you see that it is really possible to test in circuit. Okay, and we know now that our capacitor is healthy if we watch only our ESR. Now let's see what our capacitance is. And the meter is reading because it is, what did we say, 560 microfarad, and this meter is reading 619.619 millifarad, means 618 microfarad. So we have here a plus tolerance with this meter, and we test it, of course, with our component tester as well. So let's see what this meter is telling us. Again, no good contact. Oh, what's going on here? Okay, so something must be wrong here with my Kelvin clips for any reason, I don't know. So let's test it here directly in the unit, and here it is. So we are testing with 120 Hertz as capacitors get tested today, and you see we are within tolerance of the capacitors. We have always plus minus 20%, right? And yeah, you see that this capacitor is healthy, so we can of course check here for our tangents delta, and that is 75.7 degree, which should be in tolerance as well. So everything really looks fine. So this capacitor is obviously working. All parameters are in tolerance, and that means the first impression we had from our capacitor. So let's go back here to let's go back to our ESR, and now we are testing, of course, with the wrong frequency, so we need to go up to 100 kilohertz, and you see we are very close to the figures we tested in circuit, and that is more or less here the practical proof that you really can test the ESR in circuit, and you can determine if a capacitor is healthy or not. Okay, but let's go back here to this capacitor, because that is a very much the same, pretty much the same type what we had in our Heathkit IT12 signal tracer, and there we only did our ESR test. So let's do an ESR test first. So I have to use this one now. So something is wrong here with my Kelvin clips. I have to test it, what's going on there later. Anyways, so let's test it here with my other probe here, and somewhat funny here, unbelievable. So let's see if I can get a reading, and I can. So you see the tested ESR is 0.25 ohm to 6 ohm, so 260 milliohm is our ESR, and as we already said, this is 350 volt type. And going back here to our table, it is 50 microfarad, and this here only goes to 250 volt, and you see with a higher voltage the allowed ESR getting up. So we are far below 0.8 ohm, right? And that means we would consider this capacitor as healthy. And once again, let's try if we can do it here once again. Somehow it is a little bit stupid here with this probe, because of course it is not made for testing this in a way we do it here. So you see that is a little bit that's not the right way. Let's see. Yeah, so you see we can get out the reading, and let's see if I can hold it this way, and let's see if we can read our capacitance as well. And you see we can test it with 40 microfarad, and 40 microfarad is within a spec. So this is 50 microfarad, but these capacitors have 20% tolerance, and it is still intolerance even with the new test method, but in the past this test method has been used, and we see it is, let me go here, and you see with the older test method it is much more intolerance, and that is what you always need to have in mind, okay? And if we choose now another method as well, so let's see what the Sencore is reading. And yeah, you see with the Sencore we are testing for 51, yeah, approximately 51 microfarad, and that is exactly the different test methods. In the past I explained it in the other videos on electrolytic capacitors. So the methods were different in the past, and thus we have different results. But in any case, you see that this capacitor is within tolerance, right? So here with this old Sencore, it is 50 microfarad, so you would say it is a brand new capacitor, no problem at all. But still, we are not happy with our results, so we want to prove it even more that this capacitor is really working. And what we didn't do up to now is we didn't test this capacitor for leakage current, and that is very important as well. And you remember when we were working on the IT12, our Heathkit signal tracer, we had the bulbs in front of the IT12 to protect the signal tracer itself. And I was claiming that if there would be a short, then our bulbs would jump in and would protect whatever is shorting out. And that is of course what we need to do as well, because that was with our IT12 our second test. So we tested for ESR and we found everything is fine. And then I cranked up the voltage very slowly with my insulation, with my isolation transformer to the voltage the capacitor is able to handle. And I was testing for temperature, because if there is a short, then you would, or not really a short, let me simply say a resistor inside which is leaking, right? Then we would feel the capacitor getting warm. And you remember that I was observing the indicated power what our IT12 is allowed to consume, and we said 25 watt is fine. And with observing all these parameters, so what's going on with our power which the IT12 was consuming, what is with the temperature, and finally of course we were reforming the internal capacitor simply due to the fact that we put AC to our IT12, right? And we had a diode in front of our capacitor in the IT12, and thus this is a kind of reforming an old capacitor, and that is what I have here. So this here is my little electrolytic reformer set, and that is nothing else. So I just put it here on the back just to remember myself what I have done. So we have a little bulb, this one here, right? And we have a diode inside. So this is a 1N4007 diode, so simply rectifying our AC, which we get here at our input, and then we put our capacitor, our device under test, simply here in this socket, right? And you see, of course, because it is rectified, I put here plus and I put minus, and I said I'm telling here it is DC, right? And you see I've written it in. It is a 1N4007, so that is our rectifier diode. And if I have a very old capacitor like this here, I can always reform a capacitor that it is back working fine, and that is what we want to do now as well, because we want to know if our leakage current, and we know from our earlier videos that all electrolytic capacitors have a leakage current, so that is normal, but the leakage current should not exceed a given value, and that is what we want to test now. And we have our bulb in front once again to protect if we really have a short here with this capacitor, right? And therefore let us test if this capacitor is still in spec. Okay, so I have prepared now here our next test, and well, what you can see here is our little reformer, whatever you want to call it. I mean, this is now the power supply for our electrolytic capacitor, and what we want to know is this capacitor able to handle 350 volt or 300, don't remember exactly, and are we able to get it down to, we take another table, so we have 47 microfarad, all right, and we have, let me double check, 350 volt, and with 350 volt our leakage current should not exceed 164 microamps, right? 164 microamps, or yeah, microamps. So and that is here a modern table, so for modern electrolytic capacitors. So, you know, this is an old capacitor, and it is allowed to have a lot more leakage current. But anyways, let's simply check, and yeah, you can read the voltage, which are the DC voltage, which is here at our capacitor here at our cyclant, and here you can read the leakage current. So this is the leakage current in milliamps, so you can see that. And when I now crank up my isolation transformer, then you can read the voltage and the current, and what we want to see is finally an electrolytic capacitor which is not leaking too much current, right? And therefore let me start increasing my isolation transformer, and you already see that here our voltage is going up. So now we have really 14 volt DC at our capacitor, but we know it is a 350 volt type, and this capacitor should be able to handle 350 volt, or let's say minimum 350. So let's carefully crank it up, and let's watch here our current. And you see, while I'm cranking up, it is coming up as well, but then it goes down, and that is normal because the capacitor tries to handle the voltage which is getting to to the terminals. All right. Let me go up here. And you see this capacitor is really doing it quite well. So we are now at 200 volt, and with 200 volt you see we have a leakage of 350 dropping down. Once again, so it is really in the microamp area what we are doing here, right? And you see it is still dropping, and that is that the capacitor is reforming itself, because basically this capacitor seems to be healthy, okay? And that is what we can see here very, very clearly. And yeah, let me crank it up a bit more. And we are, let me go to 250, and let's observe here our leakage. Our leakage is 400 dropping, which is absolutely nice. So let's go up to 300 volt, and be careful, 300 volt can definitely kill you. So if you're following along, you are doing on your own risk. Now we are at 300 volt, and you see our leakage is 700 microamp, and it is dropping, which is really nice. And of course it would take now a while until our current is really at the right level. But let me have a look here on the table of my Sencor. So you may remember that I have here a table. I'll show it to you in a bit. And we are dealing with 50 microfarad, and we have 300 volt connected here to our capacitor. And here my Sencor table is telling us that with 300 volt 730 microamps are allowed. So that are the old values, and these values are for the old capacitors. And of course we have here an old capacitor, and we are already far below 700 micro, right? And that is telling us, according to the old figures, this capacitor is already in spec. It is not in spec up to now for our new values, our modern capacitors with yeah, I have it not here on the table, because this is the 350 volt type. So let's go up a little bit here to 300, and 50, and you see our leakage current is of course going up a little bit. That is totally normal and no problem with it. Now we are at 350 volt, okay, and you see our leakage current is dropping, so we are reforming our capacitor. Everything is fine, and I stop now the video for a moment because I leave it as it is here, okay? I really leave it as it is, and we really want to understand if you know, we are able to drop the leakage current to a value what we would expect from a modern type. And once again, from a modern type with 350 volt and 50 microfarad, we would expect not more than 164 microamps, okay? And so we leave it run a little bit. I stop it now. If there would a breakdown inside our capacitor, remember, our bulb here would jump in and would protect here our circuit so that nothing can get destroyed, okay? By the way, what we are seeing here as well, our voltage is going up, and that is because our leakage current is dropping down. So let me adjust it here a little bit back to 349, and we are at 40. So I stop it now. Okay, so now it is approximately 10 minutes later, and you see here our capacitor is really doing well. So we are here around 200 microamps, and that is really amazing with 350 volt input voltage to our capacitor. And just to show you here, so that is our input voltage, our AC, right? Before, of course, it is rectified. So that is the voltage which goes here into our little unit here, right? And yeah, you really see that the capacitor is doing well. Okay, and let's try to have here a look onto our Sencor table. Ooh, I don't know if I can get it here on camera, so let me try. Maybe it works. Let's try. So we have here 50 microfarad capacitor, right? And if we go over here to 300 volt, right? So this here is the 300 volt, and we get the information that 730 microamp would be fine, and with 400 volt 850 microamps would be fine. And as I said, that are the old figures, which has nothing to do with a modern capacitor any longer. And with these old figures, we are much better than what this table here is telling us. And again, have a look how well our capacitor is doing. So we are under 200, I would say. So you see, it is really working up and down and back and forth, and that is clearly the indication that there is something going on in the capacitor, so that the capacitor really tries to follow up, and that is what you see. And we are not far away from the value we would expect from a modern capacitor, and that was rated with, let me double check once again, with 164, and you see we are really not far away from a value for a modern capacitor, and thus we really can say this capacitor is more than healthy. It is simply just awesome. Okay, so we leave this here alone for a little while, so we let it run here, and our amps are still dropping, very nice. I just wanted to show you some really old electrolytic capacitors. So this here, for instance, is, yeah, it is written on it Elko. It is 100 microfarad, and it is 30 to 35 volt DC, and you see that is a tar electrolytic capacitor, very old. But anyways, this here, what is this? This is also an electrolytic 25 volt. You see here the plus marking. And yeah, it would be interesting to see this capacitor in our tester. Okay, and I put it here directly here into our instrument. Let me see if I can get the reflection away. And we are reading here our ESR. And what you see is 0.5, but not ohm. Have a look, it is mega ohm. Okay, so let me see that you really can see it. It is 514 kilo ohm or 0.5 mega ohm. So that means we have a real big ESR, and that is of course telling us that this capacitor is definitely not healthy, and this is a capacitor you never would leave in a circuit. You would of course swap it out, but that is now a real demonstration what's happening with an old capacitor which is really aging and which is not healthy anymore. And yeah, when we now take this capacitor and we put it here to our tester to see how many or what is the reading of the capacitance, because we expect 100 microfarad. Don't know, can you see it? No, you can't. I'm here working around my 350 volt. Oh my goodness. Okay, so 200 is he is not reading. On 20 microfarad the meter is not reading. 2 microfarad it is not reading. 200 nanofarad the meter is not reading. 20 nano, it starts reading something. Let's go to 2 nano and that is really funny. So this capacitor only has 41 picofarad left, and you see this is of course the second proof that this capacitor is really dead, and that is when you find a capacitor with a high ESR, then you can be sure that this capacitor wouldn't work. And of course, if we would put this capacitor now to a DC voltage, you may imagine what would happen. I mean, this would have a heavy leakage and would break through. So this is a real example what would happening. Let's see our second type, 25 microfarad. Let's see what our meter can read here. Let me see. Yeah, it is. Oh, you can't see it. Sorry. So it is the same. It is only 47 picofarad. And when I try to go up to the, yeah, it is still the same, 48 picofarad. And there you really see the difference. And also in modern units, in radios, for instance, we have SMD capacitors which are showing 500 kilo ohm of ESR. So remember our vertex standard vertex restoration. There we swapped out all the SMD electrolytic capacitors, and some of these capacitors also showing a very high ESR, around 200, 300, 400 kilo ohm ESR. And it is clear that these capacitors won't work, and that is the reason why this nice radio was not able to work correctly. And so you see how it hangs together. And by the way, while we are talking, you see our value here dropped down to a level where we are now within the spec of a very new capacitor. So once again, 350 volt, 47 microfarad. We would expect with a modern type 164 microamps, and what you see, we are reading here 157 microamps. That is telling us that our old capacitor is already in spec for a new one. So I can switch here to microamps, and yeah, you can see it here. So maybe this reading is already better, I'm not sure. Here we have 150, and when I switch over to micro, then I only read 78 micro, so that is even better. Not completely sure if this is now a test error, but anyways, if we leave it this way, we see it is just amazing. It is fine. Okay, so I hope I was able to show you all the different test steps we have to go to judge if a capacitor, electrolytic capacitor, is healthy or not. And we have seen that we can use, of course, our ESR to get an idea of the condition of a capacitor. So we see when the capacitor starts aging, and we know when the ESR is really rising to a high value, then our capacitance will drop down, as we have seen it here with our old types, right? So we know that if we find a capacitor with a high ESR, or even when we see it is just creeping over a level indicated in a table like this, and once again, this is a general table. The tables from our manufacturers are more accurate, and they show lower ESR values. And even if your electrolytic capacitor is exceeding these values here, you definitely know that the aging process has started, and that means you have to swap it, because it is only a question of time until this capacitor is completely failing. And therefore I hope you have now an overview what you can do with an ESR, and yeah, what you can or you know now the conclusion you can do with the known tested values, and so I hope this was a little bit helpful for you to understand it all a bit better. And therefore, yeah, let me stop the video here. Both parts together, part 1 and part 2, are really long. But I hope I was able to get all together what is important if you want to talk about ESR, if you want to understand ESR, and if you want to know what the tested values are meaning to you. Okay, so that's it for today. Thanks for watching, and yeah, if you like it, please give me a big thumb up, and catch you next time. Bye.